So this should all be recording and live, so it can be reviewed later.
All right, let's put our goggles on and you can come on up front.
So you have a stamp.
Yep. I practice it with a cold one.
Right.
Yeah.
Your laptop's right there and it's open.
Grab two loads position.
Yeah.
Best place for the torch is to be back here. And you're going to be curbing in the fire from the side because the fire is supposed to be right in the front. And that way it just kind of, because you're here, it kind of keeps you out of harm's way. And you just always want to try as best you can to angle the flame so that the flame is hitting new glass, not old glass. Because if you do asymmetric heating on old glass, you get hot spots that will cause it shattering. So, in general, you're pointing this way, 1, 2, 3, and then
You get
4, 5, 6, not 4 this way, so you're just pushing across here. So usually try to angle the torch this way as you're piling in new glass. The shattering piece, it doesn't it just cracks. Out the sides.
Yep.
I'll be able to tell.
That's a regular occurrence.
Yeah, so it's
You're going to start off.
that one has a set point. You can't go one
So
way.
we'll start off with.
You could
All of them are going to have 5.
doing that. So the crucible comes out, it starts to pour, you do a slow pull, but that's what happens. And as the string is coming out, you're mostly concentrating on the string of glass that comes out, and then after the crucible, you do fire polish the top until it's smooth out the case. Sort of some art to the torch work.
All right. Try starting.
Okay. Yeah.
5 minutes. Yep. All right, you ready? All right, open it up.
A little bit closer on the flame, there you go. And then just focus on that little bit that little nub that's sticking out, and so then if you just kind of wait, and I'd say, you could go almost good, and this is already pretty good cover. A little higher angle attack. Okay. And go ahead and stand there while it's.
Yep.
And sometimes a nitrile glove helps out with heat.
Right.
Yeah. Of course. Yeah. And so with the stamp, Typically what you'll want to do is if this is the disc, you're normally standing like
Oh,
right here at the bottom.
okay.
And and it's going to be hot now, but what I often do is take like a number. These were all 5 and then the number. I line up the dies, and if you do it right, I get a single shape to the syrup. And because they can be backwards, I often sort of press it on my skin to make sure that the actual imprint isn't upside down or backwards.
Okay.
So that looks good.
5C. But that's a huge question.
So this one's pouring out just a little bit differently, a little bit of a smaller.
So that was a copper blue. There's actually a flame reduction that happened there. I can see some copper mirror. So the carbon monoxide in the center of the flame removed some of the oxygen from the copper and donated the electrons back. So there's a copper flash, copper mirror on the surface of that one. It's actually little metallic copper particles. So that one's actually pretty cool. If you look through it, it'll be light blue. If you look on top, it'll be copper mirror.
5D. Is that us? 5. I will remember. 5. I thought we're at M.
Strike it again, you're flaming the box. There you go. And then say with the door, it's a little bit slow up, slow down. There's this brick inside of that that's pretty brittle and hot, so this little shock on top can kind of jar that, so it's kind of slow up, slow down. Otherwise, it's fine. So you'll eventually start hearing what's called crazing. There's a differential shrink rate. The ceramic shrinks at a different rate than the glass, and so it's going to start popping cracks in the glass through a process called crazing, and this will make a chorus of interesting little sounds. And if you were looking in the crucible, there'd be a crack formed every time you hear that sound. But we've already got great examples of what appears to be an iron. We've got the copper blue. We've got a manganese purple, pretty dark purple, and that is a chrome green with a flash of copper as well. That was a copper chrome, apparently. Right? E was copper chrome. So, anyway, go ahead.
5F.
So you want to strike until you get a flame. Strike again. There you go. So what's happening there with the flame is surface ignition. The hot surface of the glass is actually combusting the gas. Piezo has and stream. It's like the post fuel hits the glass and it's not quite as hot. So you see that like
5H.
pull back, re-click, and try to get the ignition from the tip, not just flame out the glass. You know what I'm talking about? So like on the hot glass, it looks like it's flaming, but you'll notice that there's a clear stream of gas until it hits the glass and then it catches on fire. That's post-ignition and surface ignition off the glass, which means it's applicable. So I can just make some here for you.
So why you actually
So they get hotter as you go through. So is the oil heating up too much?
No.
Okay. And you'll want to avoid the temptation to touch fiberglass. This is not like fiberglass insulation. This is pretty thick. So what happens is you're like, hey, look, it bends, and then it breaks and sticks into your skin like a hypodermic needle. So I'll try to safe the area as soon as we're done for fiberglass. But just avoid the tendency. It looks cool, but don't touch it. The fibers. That on the glass, on the plate, which should be small. So you have to tap it. It should this way.
5I. 5I.
So the one I just did was cobalt oxide.
Just straight cobalt. It
Yep.
must have been a light dose.
Yep. So for this next one I'm going to do, they actually went a lot lower in the silica, a lot higher in the metal content, so we should see a difference in the porability.
Stir it again. And keep firing the tree. Okay, feel free to use a welding glove. Some of that radiant heat is killer, so try to. So that's like pancake. What was that? Did that have borax in it?
I'd have to check to see that.
That's crazy flat by comparison. So that's really different viscosity. And that cobalt actually has darkened up significantly, so that's actually not as light as I
I did that actually.
Yeah, so that one I just poured, only 75 grams of pure silica, and they did use some borax in there.
Yeah, that had to have some borax.
We got 5J. 5J.
So we've got 12.
I need to put pictures.
Alright, so I'll clear this, once you get those two, and we'll get it from there. And I do see your little starting to get some radiant smoke.
Yep.
But still too hot for you?
No, not inside.
Okay.
5J.
Ready? Yeah.
We got 5L. 5L.
Maybe a little more on that bit and stick it up. That's good. Whenever you get all the way up there, really slow. Pretty good.
It's listed.
That's what we're about.
Hot. Now, would you rather pour the next one across the back or
Five. 5M.
The top left one. Top.
5 Keep looking at that replacement spring chain. Okay, that's definitely had more fiber tendency. That's crazy.
Yeah, that one a lot more viscous. Notice it came out kind of just a clump.
5M.
Definitely hit that bubble area. So you got the, so we'll hit the fire from the other side. We're the last spot of the one that's going to get kind of stable with that huge bubble that came out of nowhere. A little bit more. I think that's good. Alright, that complete the set?
That's it.
Get one on you. Fell off. One on the top of the chute. Typically now there's a couple videos, and I just remember I need to print the field trip permission or waiver, field trip waiver that we'll need to sign for next week. So you haven't printed that yet, right?
I have.
So I'll get that and bring it in. Just make sure you send it before you go.
Okay.
It's a requirement that says that you understand it's going to be some strenuous activity up and downstairs. You promise not to smoke tobacco or bring an aluminum can. That one's my favorite. The aluminum can, if it somehow gets in their glass return line and the aluminum can is the furnace, it off-gases aluminum ions into the glass, which messes up the production for about 2 weeks. It makes a stiff line of aluminum cross-linked glass, and it causes these cracks. And all they can do is just constantly remelt all the glass. They can lose 2 weeks of production from one aluminum can. So this does happen from time to time. So we'll pick up those particles and put them in a beaker. But that's the way glass explodes. Internal tension. I'll put a light table right here with cross polarizers so you can see the internal tension fields. And that's where the energy came from. The energy came from billions of little bonds that were at a non-equilibrium distance. And they're wanting to spring out, but they can't because the glass is contracted. So it's like you loaded all those bonds like springs, and then it finally catastrophically can break like that. There's a few questions about that on the lab write-up. Interestingly, we could remelt that one. We might try to do that. We can try to remelt and report, or we can just look at the colors. But it depends on what we want to do. I'll deal with that.
Alright, so while that glass is cooling down, I'll show a couple videos. There. Put back your spots.
sometimes it's the aspect ratio, that flatness. In theory, we can reset that. It's like we got glass and dead loss, which are turn into glass too. Well, it would incinerate, no question. Cremated loss.
All right, so back to the questions I had for you at the start of today's lab. Why exactly did Mount St. Helens explode, but the volcano in Hawaii just simply pours out lava? And the answer is, where did the material for the lava come from? So for the volcanoes that are on the western coast of the United States, the lava comes from melted rock, specifically the rock that was at the crust of the earth. And what are the two most abundant elements in the crust of the earth? I know you know this.
Two most important.
Two most abundant elements in the crust of the earth.
Carbon.
What do you say?
Carbon.
Not carbon.
Silica.
What do you say?
Silica.
Silica, that's number 2. What's number 1? Oxygen. What's SiO2? Hey, that's just silica, what we just put in there. So the reason why Mount St. Helens exploded is because its lava was filled in with SiO2. So you notice that the materials, or the samples that were very high in silica, very slow at pouring, very high viscosity, kind of clumpy. So for Mount St. Helens, the lava went up to the top, it cooled out, and sort of formed a cap, a very viscous cap. And what happened is the pressure kept building in the bottom part of the mountain, bigger, 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 until literally the mountain exploded. On the other hand, the lava for Hawaii actually comes from the closer to the center of the earth, and most common element in the center of the earth,
Iron.
iron.
Yeah.
And you notice for the one sample that was mostly metal, it was much more viscous. It just kind of flowed out. So, again, observations from nature explained with this class. All right. So with that, we're going to watch a few videos. So in lecture and in the lab, to a certain extent, we talk about the materials properties in terms of what can you do with them, like what can you build with. But of course, with glass, you can mess around with the properties of glass, and you can do more an artistic flavor of it too. So we'll watch a few videos here about a guy by the name of Dale Chihuly, pretty famous in the glass world.
Tell us where we are. Okay, we're at the Boathouse, Dale Chihuly's studio and home in Seattle, Washington. This is where Dale's work is made and where we conduct most of the business that he does. This is the hot shop where we have hot glass.
We first met Joe, who was telling us a little bit about why Seattle is so good for glass blowing, and it's because its climate is not too hot, not too cold.
Our glass is 2,150 degrees Fahrenheit, and that's the working temperature of the glass. In order to melt it, we put it on what's called high fire, and it goes up to 2,500 degrees to melt it. So we should take a trip to the furnace.
Okay.
That's
That's a statement I never really expected to hear.
oh no,
We're gonna take a trip to the furnace.
trip to the furnace.
So what are you doing now?
Well, I'm gonna gather this, what we call a little gather here, and the pipe kind of heats up as we stick it in the furnace there. Wow. So we have this little device to keep ourselves from burning ourselves on the pipe. Turn, and then you kind of let it fall on center. There you go. It cools off.
Yeah.
There you go. See? Natural, that's the right. Hang it down and it'll go down.
Is the burn unit nearby?
We have a little device over there that patches us into the fire department. Kind of come out.
Yeah.
And then you lift it on out of there. Okay. Up and out.
Lift. Yeah, there you go. Keep turning.
Wow.
Good. Keep turning. Good. Right now.
There you go. There you go. Now this is the marver. This is what we call the marver, and now you are marvering. Marvering the glass.
Marver is just heavy metal.
Yep.
Uh-huh.
Very good. Oh, and this is a good shot coming up here too. With this is what we call a roller wrap.
We'll return to Foster in just a second. Oh, they're applying the red to it? Right.
Yeah. And these rollers are offset, so the bubble moves down and the color goes on it.
It's like taffy.
Hale founded it.
Oh, he did?
Yeah. He was the founder of the school.
So is he like the main glass man in Seattle?
He's about the main glass man in the world.
Really?
Yeah.
I was going to school here at the University of Washington and was taking a degree in interior architecture. Started getting interested in glass, started melting glass, and one night I blew glass out of a little kiln. And then from there I decided I wanted to be a glass blower.
What we're working on today are these wall pieces, okay? And so what you see the dark bubble on the inside?
Yeah.
That's actually an air bubble with a thin layer of color that's been it right there is about to drop on to the pipe. We're going to just reheat it, shape it, and with my great team, we'll hopefully get it in the box. So,
Just stay out of your way. Where should we
no,
be?
I don't want you to stay on the line. I want you to get right in my. I'm going to have you help me a little bit here.
Martin works for me, but he also works on his own work and has his own exhibitions. And many of the glass blowers that have worked with me have gone on to develop their own careers. Some of them, like Martin's, stay around and still work for me. Others go out on their own entirely. But there are some, I don't know if anybody told you, but there's something like 50 glass shops now, glass furnace studios in the Seattle area.
It's not really glass blowing, it's more like glass shaping. But there's a lot of prep work in the shaping the bubble and very little blowing.
Well, glass blowing is difficult to get started in because you have to have the equipment.
A little further.
So you've got an initial outlay of, a couple $100,000 just to have a small glass shop, and then to run it costs a couple $1,000 a day.
Actually, what you're gonna do is these are wooden paddles and they're to protect me from the heat.
Okay.
All right.
Teamwork. Hey.
You guys are awesome.
Oh, wow. I can't believe you can even
It's a
talk.
pad of wet newspaper he's got in his hand. It's like
Cap.
50 sheets of newspaper wet with water.
Oh, my gosh.
You can do that with wet
Should it be up there for you?
Wow. Blow? Yeah, shoot my chin. Stop blowing. All right, good. Level. Tip up. Right here. Don't stop on it.
This climate is conducive to glass blowing because it's not too hot. The only really bad climate for a glass blower is a hot one.
When you blow glass, you blow the bottom of the vessel first. And now we're going to break it off the blowpipe. Okay, cool. Glass always breaks at the coldest spot, right? So just a little drop of water here, drop of water there.
Yes.
Boom.
Wow, there it is.
Is that cool?
What you saw down there was those techniques have been used for 2,000 years.
Squeeze them together so you get in. Good. Now push down.
Okay.
Good. Hit the lip pad with one paddle. Good, man. You are on the ball.
I'm just pushing down.
Push
I can't
harder.
even see
Push
it.
harder now.
Yeah.
Ease into it. Push harder. Push. Let them open up. Good. Push. All right. Now, when it starts to feel like it's not moving anymore, you're done. We've got as much work on that heat as we could. Now, come out. Good job.
Whoa. These
And
were
these
on
things-
fire.
And
That
so
was
with
fire.
Full heat. All right. I'll take those.
Okay. So what's that?
That was good. We got about 2 heats left.
Okay.
What we're doing now is we're going to peel this ball open flat to make the wall piece.
All right, so these are coolers for it?
Here, well, yeah, essentially their ovens are 900 degrees. The timing is just critical on that because you've got about, while it's heating, that all the work we all were doing comes down to that very last heat. That's where the shape is made, that's where the beauty happens, that's where the nuance, the delicacy of the whole piece. All that work is just for that one heat. And then in a few seconds, you come over here, and if your timing's off, crash, it falls on the floor. Where do you get your inspiration from?
I'm lucky in that the ideas come to me. You know, I probably don't run out of ideas. You know, sometimes you wonder if you run out of good ideas. Glass is a lot like water. You know, there's a lot of, I like water, I like glass, I like ice. There's a lot of characteristics. And it also kind of works like the ocean, makes forms like the, you know, there's some connection between all of that. So I end up blowing glass and stuff, everything. Half the stuff I make looks like it comes out of the ocean, even if you don't want it to. I like the rain. It's really, I find it conducive to thinking, and I always tell people, gee, if you had to write a book, you know, you want to go to the Caribbean to write the book, or you want to go to Ireland, which is a lot rainier than Seattle. And where are they going to write the best book? Even most people admit it's going to probably be Ireland. Somebody is an aspiring glassblower, where do they want to go? They want to move to Seattle, because here we've got, you know, more glass activity than anywhere else. I mean, Venice has more glass factories and furnaces in Seattle, but it was second to Venice. And I think I would be proud to say that we probably have more glass artists.
Couple thoughts on that. The color. Anybody pick up the color of that glass they were using? Happen to know what metal you think that might have been? Anybody? Was that purple color? That's a manganese glass, just like 5D here. So you can just tell there's only a few metals that can make certain colors, and so that was a manganese dope, just like this one. You'll see that purple color later on. People often ask, can we take the glass home with us? Well, you can see what happens. They shatter, but they were using annealing ovens at 900 Fahrenheit. What I'll be doing is we'll take the glass, load it in that second thermaline furnace on the side. I'll keep that at 550 for a few hours and then do a slow cool. It'll relieve internal stress, and so those will be stabilized, but not this week. That would be probably next week or the week following. But we will stabilize this glass, and I'd say most of them make it all the way through the annealing process. I am reheating that borax glass, and we will be able to re-pour that here in a moment, just to give it a second chance on life.
Yeah, just a comment about what they're doing. So they take raw material, it's like what you did, heat it up, melt it, and then it's this range in between the glass transition temperature and the melting point where they work and they can shape it. So it's a liquid, but it's a viscous liquid, so you can put it into a shape, and as you get closer to the glass transition temperature, it will hold that shape better. Then, of course, if you want to do more work, you usually have to heat it up a little bit more, then work on it as it cools down, heat it up. You saw them pulling it in and out of that furnace. And in case you're wondering about Dale and his eye patch, it wasn't actually a horrible industrial accident. He just got into a car accident and lost his eye that way. So it wasn't actually the glass working that caused it. artistic side of things. And the Jehuli Institute has made a lot of just for various things. Again, you can see this entire tree-like thing is made out of glass. This one, again, made out of glass, presumably where it doesn't hail because it's outside. Alright, so that's more the artistic side of using these materials. Of course, there's the more practical side. So here I have a video about making glass bottles.
You might never know how glass bottles are made. In this video, you will learn how Rotel produces bulk glass bottle. Step 1. Raw material preparation. Raw materials of glass bottles include sand, soda ash, limestone and pellet, recycled glass. All of these raw materials are sourced from certified suppliers and go through incoming quality check before being used in the next step. Step 2. Batching mixing. To bring a glass bottle design to life, the mixing portion matters. To make sure consistent quality of all batches of the glass bottle, the mixture portions have to be accurate. Step 3. Melting. The mixed raw materials are now being molted in the heating furnace under 1600 degrees. In this step, we get melted glass called gog, the original condition of a glass bottle.
So basically,
In a glass bottle factory, the glass furnace always worked 24 hours a day, 7 days a week to make sure stable temperature and reduce energy waste. Step 4. Blow glass forming. The molten glass are then molded into the desired bottle shapes in the blow forming process. There are two types of forming process. For narrow glass bottles, such as beer glass bottles, wine glass bottles, or soda glass bottles, we use blow and blow process. Compressed air is blown onto the molten gog and pushes it to take the shape of the mold. This initial shape is referred to as a parison. The parison is then flipped to an upright position and injected with more air to fully define its shape. For wide-mouth glass containers, glass vases, glass candle jars, or milk bottles, press and blow process is widely used. When the molten gog falls into the individual section, a plunger pushes it to fit the mold. This action defines it into a parison, which is then transferred to a blow mold. There, it is reheated and blown with air until it is properly shaped. Step 5. Annealing. The glass bottles are moved into an annealing layer, a long kiln. In it, the glass bottles are slowly reheated and then gradually cooled again to a temperature below the strain point of glass. Step 6. Quality check. We combine automatic check and manual check to make sure that the glass bottles successfully pass an inspection of functional standards. Experienced QC can detect any flaw at the first sight of the final products. The manual checks on finishes include split finish, crumbles, deformation, molded seam, out of vertical finish, hammered appearance, thin walls, blisters, Forward.
And any ones that don't pass the quality check, we just take the glass, throw it back at the start, melt it down. A lot easier just to take glass and heat it up above the glass transition temperature than it is to make brand new material. So that's why they reuse so much of the glass. It doesn't pass the QC.
Step 7. Surface treatment. Surface treatments are performed on the exterior of glass bottles when they are complete.
So again, lots of different uses for glasses. This one they're turning into what this one is. But again, you notice that the factory's making just a wide variety. All right, and I don't know if Dr. Ray mentioned this in lecture, but next week for the lab, we are going to go and tour a float glass plant here in the Manama. It's not required if you don't want to go. I think that's fine, but it's a really cool opportunity. I think you should check it out. So we're going to be going to Cardinal Glass. Cardinal Glass, it's over by the interstate. I think it's by exit 45 if you're coming off the interstate. But to get there, again, we leaving Stout, okay, go up past the hospital, taking Highway 29, and then you turn here and then go north. And it's actually on the opposite side of the interstate, right there. When you get there, you might be tempted to sort of pull into this area, so you'll be coming in from this direction. You might be tempted to pull into this this spot right here. That's not where the parking lot is. You're going to actually want to go up and around. The parking lot is sort of in the back of the building there. But if you do want to end up going, you are going to have to sign a permission slip. Dr. Ray's getting the permission slip right now. Basically says that there's going to be some mild walking, so you have to be prepared for that. Of course, no aluminum cans, anything like that. Has anyone ever been to a float glass plant before? All right, really interesting, fun time. Alright, so I think I've spoken for long enough. Alright, so we have your samples up front here. It's a little bit warm, but still touch it. So once Dr. Ray gets back with the permission slip, you can go ahead and sign it so that you can go take the field trip next week. If you don't have a vehicle, talk to one of your classmates. You can see if they can give you a ride there. If all else fails, I can give you a ride. And I think we'll try to meet there at about, class starts at 9:05. Meet there maybe about 9:30, 9:35. So that gives about a half an hour to get, if you got an 8 a.m. class, to go ahead and get a trip down there. All right, so with that said, go ahead and come up and make observations about the glass. Dr. Ray's going to go grab a light table. The light table will allow you to see the internal stresses on the glass. We just need to use some cross polarizers. So once that light table appears, go ahead and take your sample to the light table and sort of observe the internal stresses on the glass. I'm going to leave this up for as long as it stays up so you can see what the different batch formulas were. And of course, wear your goggles in case your sample accidentally blows apart your hand. With that, good luck. sure to get your pictures too.
She turned out a really nice green. I couldn't see it in the card. That's really pretty. Did he explain the like bronze at the top? Like those being supposed to be copper.
So they should be stamped with the different letters and the list of the formulas.
Talk to the guy that's staying.
I don't think I have enough spots for all of it.
Mm-hmm.
Yeah, but I don't know.
Doesn't look like a C. I would say.
I do a good job.
Color
Did you use? You're helpful.
I'll get the pen right down here in just a second. I would say I'm going to file off this tail right here. So that's like a scorpion tail. Be careful with that. So I'll file the sides quick so that can be picked up safely. And most of them look alright, but they're still just enough heat that it kind of hurts the touch. I'll file that down here just a little bit. I'll find those polarizing films. And then this is the form that usually I put in my name is Stout.
Yep. Yeah.
It's like a light.
He said he took a shower.
Well, this one
This is the second time in 2 years that that's happened. It happened last year as well.
All right, I got the sign-up sheet for the, I should say the permission slip up front here by the ruler.
A little bit.
Wait, so yours exploded? On your sheet? On the sheet.
We're done seeing. Yeah. Okay.
I can't start to help you with it.
So there is no. And then there's
Oh.
Yellow. Yellow. Navy blue. I'll look at it. Yeah, very, very dark red.
Oops, sorry.
That's not that high.
No, I do think it's. I did 8 throughout.
It's light yellow.
So, no. Just be careful with one with that. Yep.
Millimeters? 62 millimeters?
Sure. 62.
Okay, next one. Tail. $65. 65.
Yeah.
Yep.
65.
Perfect.
Also 65.
Looks like everyone.
Skip.
Yep.
see, the fluxes were either sodium carbonate or washing soda. Looks like everyone has sodium carbonate. For some people, all sodium carbonate.
Tearing the place apart looking for the stones. They're right underneath there on that tray. It's like they're right underneath.
Where'd you find the tongs?
They were on
the
this-
cart?
They were on the cart in the next lab. So it's like everything I want is on this cart, and it's like all I do is park it in another lab. I'm like, where's my stuff? So, but here's the. I showed you this last time, right?
Yeah.
So he's really great. So that's Robert parallel. They get a little bit scratched because of the glass that's put on there. But what I often do is put it on a watch glass and rotate it down. Change it. What I encourage students to do is take a picture of their current stress field and then compare it with the
But
post
they're using the lithium on there, and no one needs potassium.
I should probably chip off.
Also calcium or magnesium matters.
Yeah.
I don't see magnesium carbonate on here at all.
So that one will get a second chance here.
Calcium carbonate would be a
Try to
flux
rub that
stabilizer. Oh, dolomite. Yeah, okay. So I guess we'll just write down which of these three each person uses. Actually, okay, so.
And you might need to get one that hasn't flared.
Alright, so I got the light table ready to go. The light table uses two of these polarized screens. Just go ahead and put your sample on the watch glass. Then put the other polarizer on top of it. You should notice there should be some lines inside your sample. Those are the stress lines. And go ahead and just turn the watch glass and you can see that all the different stress lines in the sample. And I recommend taking a picture now and then take another picture after we do the annealing step to compare the different stresses in the sample.
And I'd say, I think I've gotten all the fiberglass and shards or sharps removed, but I'd still wear your goggles. These things can shatter up to a year randomly after they're poured. I did have one shatter just in my office sitting a year after it's poured. It's crazy. So wear your goggles when you're doing those observations, but that'll all be no longer a problem after it's annealed. But we'll pull those samples over, pour that sample that shattered, give it a second chance, but I think these are ready to be measured and ready to go.
Dr. Dawson, for the concentration by percent weight, do we use two different ions? Do you want just the total number?
So those concentration numbers are on the spreadsheet.
Yeah.
Off to the far right.
Yeah.
So there's actually, is that what you're asking about?
He's if they got two or more ions in there, should they do it individually or
Just
combine?
comma, and just
Okay.
kind of add them all in the same line. Perfect fine.
What about the, I guess the other letters are from the other section? X, W, T, R, U. Oh. Yeah, that was Cool Labs.
These don't line up with what's on the
I think it's supposed to be like.
I can assist with
I think the more kind of smaller sized ionic flux you use, the more viscous it'll be. Based on your yeah. Where that one has there's one about identity of flux.
Take it, Matt. No, I'm already done. Maybe we'll skip this. Maybe we'll skip the stamp on this one and let it be a perfect disc. All right. Since we know it's prone to cracking, sometimes that asymmetry initiates the crack. So we'll let this one have a symmetric disc, and I'll fire it longer to try to get a cooler down gradient to relieve that stress. Not quite as big as it was last time.
So is it smaller this time?
So it's possible that we didn't quite have as aggressive of a pour, or maybe it wasn't quite as hot because it was maybe rushed a little bit until we reached temperature. So this is probably a temperature related effect more than anything. If this was also a sample that was in the back of the furnace, or no, this was toward the middle. So I think it wasn't a temperature effect. It also wouldn't surprise me if there was a big chunk somewhere that I missed. So it might have been less volume. But I'm thinking this will survive now because I gave it lots of extra firing, which causes it to go through the strain point at a much slower slope, so it had a chance to relieve some of that bond stress. So I think this will survive. We also didn't stamp it. Sometimes those surface imperfections in the stamp cause force to kind of focus on those things that make the surface asymmetric. You'll see some of that force focusing on the cross polar right here. You can see the internal stress field. So we'll see what this one looks like.
Oh yeah.
Yeah, I think this will survive. Yeah.
Or is it really black?
So this is black.
No, this is purple.
Okay.
Like black.
Yeah, it's amazing how most colors fade to black. You end up with too much of the ingredient that just absorbs too much of the light. So yeah, it's nice and purple. Sure, I mean that's another, I guess, manganese example, right?
I do have enough.
L did
0.5. Okay. Yeah. Well, I think you'll be able to probably. It'll be dark though. See. Yeah.
Yes, that one was made.
There's a lot. It also depends on what your purpose is. Like you see, as a glaze, thin layer on ceramic, that makes a nice thin. But as glass, you have to cut back because the path length for the liquid is sort of a lot longer. Just be careful with these items. These are still quite hot.
Viscosity and
Actually, there could be a spot because of simple runoff that I did that boring glass is so drip on the lid. It looks to me like I might have hit a directly drip from the crucible. Yeah, there's a run down the side, so I probably just did that right very end. But there's these little spots that'll hit the ceramic or hit the fire brick, and they just start kind of eating in and eroding. So I have to re-brick that correct.
Otherwise, all the other ones. If you want meshes,
I have, you have calipers of your own.
Oh.
People usually use rulers, that works just fine. But you have sometimes a couple folks that bring calipers and just call them out.
So that works as well.
That also works.
So, grab it. I'll measure them. I feel like it's not fair to thank you though. I think all of them.
Yeah, don't
So
touch that.
syrup would be high.
Include as a shatter. Probably closer to 60, probably 80.
I think that's what you did.
So always think it's yeah.
So every thing for like a except for eye, right?
So there'll be some subtle differences, like you can usually from your measurements see that, and honestly, A that's being referred to there is an old standard glass that you used to use. I'll put a few of those out, but I would say view these questions as fairly qualitative. So people often say higher or lower than average. You can benchmark it like semi-quantitatively by doing sort of a 1 to 10 scale of viscosity, but in general, when you take your diameter measurements, you have to think about the implication that if it's a small diameter, it was a high viscosity glass that poured slowly and made sort of a thicker piece. If it is a very wide disc, then it was low viscosity glass because it sort of spreads out once it hits the surface. You can sort of use your ruler measurements as an indication of viscosity, but that's not a direct measurement. That's just sort of a meta type measurement where you're just looking at the implication of viscosity. You can also do things like look at clues in the video. We'll have a video posted on a playlist for the pouring sequence, and you can often see how clues like when you tip the crucible, how long does it take before the glass starts to emerge. As it bridges from the crucible to the metal plate, how thick is the glass as it pours out? All these things are sort of coding visual clues of viscosity. Diameter is usually the go-to for figuring that out. Okay.
Can we observe this one?
Yeah, you can just be careful. It's probably still hot enough to melt the ruler. But sort of cover it above. It's still.
There's a
That's still probably 300-400 degrees at
Celsius.
Did they take the reports on?
they have a Thursday morning lead hit, so you think that the drill now.
How do I get this thing going?
Maybe you would have set that up before.
Okay.
Unless you're familiar with OBS, Open Broadcast Software, it's kind of a little song and dance to set it up. But it's a streaming software that just pipes into the YouTube channel, which I use to record everything. So I'll have an overnight feed so we can check that it's still alive in the morning, so I don't have to like scramble and figure out how to do it. If it was really close on time, there's not a lot to do. If it had a breaker or something that failed, that maybe reset. Or if there was an element that failed, I could heat up another furnace and slice for the samples over in theory. Or you could just wait for the next week. That kind of thing. But I usually do monitor a couple times overnight or early in the morning. But then the feed, I cut that one so that it's not too long of a feed, and then restart it so it's just what's happening in class, so that can be reviewed by the students. They can see how their glass poured. I'm assuming you kind of watched some of those in the past. There's a bunch of them on the playlist. But I'll take care of it.
Okay.
Which ingredient and we serve this class for?
I think it might have made it longer already.
Oh, you'd be jealous. Yeah. Take me on the 60 a year. No, because you'd be making. Say that again?
Lower viscosity.
Nobody else did. I don't think he did. Does nothing of that.
Okay. Because it disrupts the crystal.
80.
No. Oh, right. There's like a thing on the front that shows it.
Yeah, that's my question.
One with a pound and one with.
We need to go back. The what we recorded here for what's A, B, C, D, all that is. Just you know all the numbers.
And
yeah, I know. We just need to know.
I mean, I'm still going next to.
We just.
It's okay. I was trying to like keep things in my order since I messed them all.
Sure.
Different order.
Some of the stamps are really hard. That's A. That's A. That's A.
Year out.
Yeah. I did.
It's still hot, so it just keeps. I know he fills this.
And then the letters got skipped. It wasn't full 6 months later. I'd say look at the firing diagram and see which one's skipped. Zero. Yep. Thank you.
There we go. That should. Okay.
So you want to put that in between. And it works best when they're crossed, so it's dark. That way you get most contrast and the light coming through. Yeah, you get this band pattern, and that banding, the tighter it is, the higher the stress field. The more spaced they are, the lower the
Picture. I have things.
Is it kind of hard to see what the
Yeah, I think I did.
You can hammer the head of it.
I mean, you can with me still.
Well,
You can probably.
so once I get these lined up, you may be able to do a color comparison.
Still on top.
Get a pretty good station.
How can internal stresses be controlled to produce desirable properties in the lab?
Try to edit it in the actual word.
So we've been occasionally checking the status of Jupiter. Just talking about the different positions, how rapidly they move positions. And so it's just been sort of a side project. So my research students are still up here kind of late, and the stars start coming out. So it's like, well, there's a bunch of unused telescopes, and so why not? So yeah, so occasionally that one, dialing in Jupiter. Jupiter's perfect if it's then it's the right position to look, and I think the glass would probably
The weights are right.
struck, but as long as it gets past a certain angle, that glass is currently parallel flat.
It's everything else is lower.
There's all the plans, the stripes, and the 4 gallon engine with right. Yeah, that's why I take it. want to observe a shorter
Did we take a picture after it was video? Otherwise, yeah.
I am surprised that it didn't even slightly.
No.
Maybe one of which is kind of I think either one works. I'll try now. There was something in that,
You know,
that on the side or something just kind of.
I think it depends on the seam. Like, I wonder if that one is. So, because of course, that's like occasionally, I should have mentioned that the mortar and pestle can't help homogenize the batch.
Okay.
If you look at sort of krill material, you see that.
Yeah.
Globular, especially if that was silica.
Array.
They use powdered silica. Silica clumps don't melt out
Well, not
very well. Flux. So this looks like it could have been some little bits in the edge here. Didn't get sufficient
Remind the
flux.
professor to
and
pass
also sometimes it
request
looks
for
like,
it.
but you see how a couple of them have it. I bet you there was one of the bags that had a little more.
I didn't see the permission.
There's such a variety, it's hit and miss.
Yeah.
So it looks like a particular ingredient would have benefited from some more pestle treatment to homogenize that powder. It still melts out once it gets in.
Yeah.
But, yeah, clearly there was something a little off.
Kind of doubt that.
So I just remember that was, all finished.
Yesterday in lecture we were talking about reducing iron oxide with carbon monoxide, and I was kind of confused as how the electron flow works, so that the carbon dioxide would also be formed.
So you go on the carbon monoxide,
Yeah, carbon monoxide and iron 3 oxide to
Yep.
make elemental iron and carbon dioxide.
Yep. So carbon monoxide